Can you hear me online? Yeah, cool. Thank you. Here we go. Time we got. Okay, let's wait a few more minutes. There's a few more people there. So last lecture, we went through the number average weight measurements. We're going to finish off the weight average measurements, the viscosity average, and then the Z average measurements today. And then hopefully we can make a little bit of an indent into module 5, which is all about the structures and properties of those structures. Sorry, the structures of the polymers and the properties of those polymers. So we saw the turbidity equation last lecture for calculating the weight average molecular weight. So so we talked a little bit about the refractive index, right? So the refractive index is a good measure of the turbidity. The refractive index is a measure of how much the speed of light is reduced through a medium. So the refractive index actually, let me just get this up. Straightforward. Speed of light. Speed of light through a vacuum over the speed of light through a material. So as the refractive index increases, the speed of light decreases through the material. There are some RI values there, refractive index values for the common polymers, which range from 1.3 to 1.7. Interestingly, if anyone has a 3D printer, Peak is actually one of the up and coming 3D printing filaments that you can buy. So what we want to do is generate a plot in which we can measure the turbidity. And one of the ways of doing this, there are a few different ways, but one of the ways of doing this is through a Zim plot. So the Zim plot measures the turbidity as a function of different concentrations and different angles. So you measure at least 4 different concentrations. And then you measure around about 4 different angles. So you can see there's typical angles here as 0, 45 degrees, 90 degrees, and 135 degrees. Now, you can actually compute what they call a partial Zim plot. And in the partial Zim plot, it's created if only one concentration is measured. So it's not as accurate as a full Zim plot, but you can still get a measurement of one concentration. Now, the way they do the measurement is fairly simple. What they'll do first is vary the angle. Hey, I've got that symbol right. And then they'll hold the concentration constant. So by varying the angle and holding the concentration, they build up this network down here. And then what they can do is hold the angle and vary the concentration. So they start to get these ones across here. So what you do is to kind of build up this network, or kind of a validation network, if you like, which then we can extrapolate down to angle equals 0 and C equals 0. And we do that because as soon as we cross the intercept, that is where we're getting the 1 over our number average molecular weight. That's how we're going to calculate it. So it works very similar to the number average molecular weight there. Now, Z average is very straightforward. So they use ultracentrifugation to do this, and it can measure to indefinitely high molecular weights. It is the most expensive and intricate instrument to measure molecular weight. I would say that one of these probably costs in the region of about $50,000 for a lower end $1, and then probably upwards of about 500,000 if you want something a little bit more technical. I know that because I got a quote. And then, so what happens is sedimentation occurs under strong centrifugal force. Centrifugal field, and the polymer chains distribute themselves perpendicularly around the axis of rotation according to size. And everyone knows really how a centrifuge works. Done those. Interestingly, it's called MZ because Z is German. Well, centrifuge is German for centrifuge. So that's why I believe it's called MZ on there. So you can calculate it using this equation. So that's where N is a refractive index. C is the speed of light in the vacuum. And V is the velocity of light. So what they do is they can couple the Z average molecular weight, the ultracentrifugation, with light scattering to get an idea of the concentration. So you can measure the different layers after sedimentation in there. So it's very straightforward. The sample is put in a rotor. The rotor spins at a 60,000 RPM. Your typical centrifuge is around about 14,000 RPM maximum. And then the index of refraction methods are used to observe the concentration gradients in there. Now, for viscosity average, well, actually, for the number average molecular weight and the weight average molecular weight, we know before that we were measuring colligative properties and light scattering methods. And both of these are direct measures of the average molecular weight. And so you don't make a comparison to a standard. We don't run a standard first and try and compare to that. So MN and MN and MW are absolute average molecular weights. However, they can be slow and expensive. And we've already talked about this, right? We talked about the number average molecular weight being measured by membrane osmometry. If we're doing it by a static method, it's going to take a lot longer than a dynamic method. But I bet it costs a lot more money for a dynamic instrument rather than a static instrument. So it's slow, right? So to upgrade that will cost some money. So viscometry and gel permeation chromatography, they're important for measuring this viscosity average molecular weight. And they determine relative average molecular weights. So what happens is when you do an experiment like this is you calibrate it or you compare it to the standards. And that's the standards of polymers of known number average molecular weight and weight average molecular weight. And it's determined by some absolute technique, right? So they're looking at the polymers which are confirmed by colligative and light scattering methods in there. And the essential thing is that they also have to have a low polydispersity index, so they can be trusted to have a very narrow peak in there. So if we look at this is a table right at the start in slide 1, you'll see that the listing for chromatography and viscometry, they are listed as calibrated for the type of molecular weight average they're calculating. So in viscosity average, for an intrinsic viscosity measurement, for measuring the viscosity average molecular weight, a dilute polymer of concentration of around 0.5 grams per 100 milliliters in solvent is used. And what we do is we measure the flow time of a polymer solution through a capillary tube at fixed length versus that of a pure solvent. So we're comparing our solution against a pure solvent in a capillary tube, which has a fixed length. And what that does is it measures a solute's polymer contribution to the viscosity of the solution because we're directly comparing it. So we don't directly measure it, we have to calibrate. So what you can see is this image here shows that when you've got the relative velocity of the solvent in the capillary, it drives the polymer down the capillary, but the polymer will experience rotation as it does so. That rotation would obviously change the viscosity of that. So here's a question. So how does a polymer in dilute solution increase viscosity of a solvent? So is there anyone who can offer an answer to that? Dun, dun, dun. Anyone guess?
What was the question?
So on the slide, see it says, how does a polymer in dilute solution increase viscosity of solvent? You're close. All right, so the answer was as it moves through the capillary, it restricts flow. And you are so close. What it actually does is that it does restrict flow, but it actually restricts flow because the shear rates of different part of the chain interact differently with the capillary tube itself. So if you can imagine, as the capillary is rotating across the capillary tube, it's going to affect the shear rate, which will increase the viscosity of those things there. So let me write that down. So it says, depending. So depending on how close to the wall of the capillary tube, the polymer chain sees different shear rates at different parts of the chain. This causes rotation of the chain and it increases in the viscosity. Give you a couple more seconds to write that down. Good. So gel permeation chromatography and size exclusion chromatography, this is a different one to what we wrote before, determine the relative molecular weight and the molecular weight distribution. So they can be useful for finding out what we now know is important, the PDI, the polydispersity index of a polymer. So it gets calibrated or compared to standards. And there's separation of the polymer based on the size. So we're looking at the hydrodynamic volume. Now the mobile phase is the solvent. And the stationary phase is a column packed with porous material. And what happens, as you can see down here, is that this is our mobile phase moving this way. And we've got the polymers of different sizes within that solution. The small chains actually get trapped in the pores of our stationary phase, which is our porous material, where the large molecules pass on through. So the small chains get trapped and the large chains elute first. So we get the biggest chains coming out first and the smallest chains coming out afterwards. I've actually put a YouTube video on there. It makes it a bit difficult to set up in here for me to show it in class because I have to change all the audio settings around, but have a look at that because it shows you how these columns are constructed. So the main thing is we're getting the small molecule, we're getting the large molecules off first and we're getting the small molecules off last because they get trapped within the pores of the porous material. Now, the way to calibrate this system is to use a polymer with low PDI. We know that already, right? We've got to use something with a relatively narrow distribution of sizes. And we need something of a known absolute average molecular weight. There is lots of different standard molecular weights that you can use. 5 to 12, well, it says 5 to 12 there, but I imagine this is expanded now to quite a few different standards. They vary from everything from 500 to 5 million grams per mole. And those are beads, which are such as polystyrene, polymethyl methacrylate, PEO, polyethyl oxide. And the PDI of those is less than 1.1, so you know that they are pretty narrow. So if anyone has done chromatography before, it actually works in a very similar way. You may have experienced this in some laboratories. Generally in labs where they're making new materials, they'll have to clean up those materials. Chromatography is the most common way to do it. It used to be that you had to manually pack a column and run your sample through, but now they do it automatically for you. So chromatography is a big industry hit because it's pretty quick at separating things out. So what they do is they inject a dilute standard solution into the gel permeation system, and the standard goes through the column. They obtain the elution time or volume versus concentration from refractive index and light scattering, and they make a calibration curve, which is elution time or volume versus the log of the molar mass. So you can see what they've done is they've ran through their solution, which contains all these different weights, molecular weights of the polymers, and then what they can do is deduce a curve which you can match your sample to. The main thing is that when you're doing these calibrations is that you need it to be in the right range for what you expect your polymer to be. Otherwise, you're not going to be in that, you're not going to be able to estimate the size very accurately. So once you've got your calibration curve, you inject the dilute polymer into the column. You go through the same steps. You obtain this elution time versus volume versus concentration from the refractive index. And you use that standard calibration curve you calculated before to convert the elution time volume into molecular weights there. This is pretty much exactly what you've seen before. You put your sample into the top, that starts to flow down the column. You can start to see that the green bits are getting separated from the red bits. The red bit comes off first, and then the green bit follows afterwards. I'm calling that the green bit because I don't actually know what that is. It's just dots. The green dots come off last because they're smaller. Really straightforward. So one common porous material that they use is PL gel, which is this image down the bottom here. And you can see that they have different sized pores on the surface. So they'll be matched to whatever polymer sample you want to separate out. They have what generally happens is they have a catalog of different size ranges, and you would pick the most appropriate gel to put into the column. So PL gel is a highly cross-linked mix of porous polystyrene and divinyl and benzene matrix. So if you want to, this is our divinyl benzene. Oh, let me, God. For a chemist, I get really bad drawing these. That's dive. Now, the interesting thing about this, and this will become more apparent to everyone later on during the course, is the importance of having these two functional groups on this side means that it is capable of cross-linking the networks. Now, that's obviously related to styrene by the addition of a second vinyl group in there. So you should know what polystyrene comes from. Oh, sorry, we should know what polystyrene looks like. But this is just a flow through the system. So you have the mobile phase, which flows into the solvent delivery system. We have an injector or an injector port, which accepts the sample. It's ran through a column, it hits a detector, and the detectors can be configured to measure a whole host of things, such as UV light, absorbance, and then you have a data system which will generate your chromatographic plots. Okay.
Excuse me, Dr. Moppert.
Yeah.
Is this PL gel a stationary phase?
Yes, the gel is the stationary phase, yes.
Okay, thank you.
No problem.
Also, I had a question. So when we're injecting the dilute standard, are we including like multiple standards, or is it just the same?
Yeah, that's a good question. That's a good question. So actually, I believe you can buy them as single standards. So you could buy them as a single size, or you could probably buy mixtures depending on the size range that you would expect your polymers to be over. So I imagine that now the suppliers have kind of caught on to the fact that people don't want to be mixing their own polymer standards together. So I'm sure you can probably buy them mixed together already. Does that make sense?
Yes, thank you.
No problem. It's quite good, this system, because it can if people speak. So the simple thing that we can get for this is that we can get the PDI of the polymer, so we can know what the dispersity index is there. So just a quick question, which peak on there has the lowest polydispersity? Just give me the number. Three. That was a silent three. Three, good, yeah. So the 3 has the lowest PDI on there. But we can understand the distribution of these polymers using the chromatographic methods. Now, there are some limitations, and limitations exist with all kind of measurements and instrumentation that you have in there. One limitation is that when we use a standard, so we might use polystyrene, which is dissolved in toluene, and you know now that it can dissolve in toluene because these solubility parameters are less than 4 between them. If we take a sample such as PDMS, however, now the difference between PDMS and toluene is not greater than 4, but you know that it's actually probably not going to be a great solvent in comparison to the polystyrene dissolved in the toluene. So there's a bigger difference in those solubility parameters for those two. So the poor solvent will result in a decreased hydrodynamic radius. So because we're putting a poor solvent with our polymer, we're going to cause our polymer to coil up and contract. So how would the difference in solubility affect the gel permeation chromatography based molecular weight measurements? So have a think about that for 30 seconds or so, and then tell me if you know the answer. Okay, so what happens if we have a polymer in a poor solvent? What happens to the polymer?
It will be extracted.
Yeah, so it coils up. So you get tighter coils in there. In tighter coils, what interactions dominate? Is it the solvent polymer or the polymer polymer interactions?
Polymer.
Yes, polymer interactions dominate. Which what happens then to the hydrodynamic radius? Is it smaller or is it larger? Smaller. So the hydrodynamic radius is smaller. Now, if we make the hydrodynamic radius smaller, what would happen to the elution time of that polymer in gel permeation chromatography?
It will be increased.
Yeah, so I think you're right? So, sorry, I'd slower in the class and longer. Yeah, so it's going to increase the time, right? Because you know that those smaller coils are going to get caught up in the porous material, which we're using as a stationary phase. So that's just logical to work through. So if you have a poor solvent, we have tighter coils. And that's because the polymer-polymer interactions dominate. Results in a smaller, oh, let me write that again. It's Monday morning. Which means it takes longer to elute. Pretty straightforward. Good. So here's one that you can practice. So I'm going to give you a couple of minutes to complete this one. So this is a practice problem. We do put very similar practice problems on exams. So just have a think about this. So draw the expected GPC output of a polystyrene standard, 5,000, 20,000, 150,000, and 500,000 gram per mole with a PDI of 1.1 with axis labels. I'll put the axis labels on for you. Then overlay the expected GPC output of a styrene sample with the following populations: 28,000 grams per mole PDI equals to 2, and 134,000 grams per mole PDI equal to 1.5. you a couple of minutes for that. I tend to get my steps up. So you may have noticed, actually, I've only started posting the notes in PDF format. Are they okay in PDF format? The PowerPoint format takes up so much room. But let me know if you'd prefer the PowerPoint format. It just takes so much room. It's so much longer to load up. One more minute and I'll go through this. Okay, let's go through it. So the first one, draw the, hang on, my wires fell out, yeah. Yeah, you still can see my screen good. Sorry, the cable fell out. So first one, draw the expected GPC output of a polystyrene standard, 5,000, 20,000, 150,000, and 500,000. You should know that the 500,000 is going to come off first, so it's going to look something like this. Interestingly, we don't know the intensity of these things, so we just draw them pretty much equal. And then we're going to get 150,000 coming off there. And these are relatively narrow, right? Because we know that the PDI of these things is 1.1. And then further down, we're going to get 20,000. Again, the intensity doesn't matter of these things. And then we have 5,000. That is the best one I've ever done. So they all look like they have a PDI, which is around about the same. And then we have the actual sample that we're going to lay for polystyrene sample. So this is a sample, not the standard, with the following populations. So we know that 28,000, let me just label these others for us. So this one is 500,000. This is 150,000. This is 20,000. This is 5,000. So we know that the 28,000 and a PDI of 2. So 28,000 is probably the peak is going to be somewhere around here. And then for the 134,000, the peak is going to be somewhere around about here. So what we can do is we can have a look at the PDI of the 28,000 is 2. The PDI of 134,000 is 1.5. So if we draw a line, so the red line is our actual sample. We just want to draw it a little bit broader. That looks a little bit broader than our standard. And then this one has to be pretty broad because the PDI is 2. Okay, so that will be labeled 28. Sorry, wrong one. 134,000. This one would be 28,000. Okay, so good. So what you can do to make sure when you're in, if these ones come up in the exams, is label these ones. Just so we know exactly which one you're talking about. Okay. Straightforward. And I think that is it for this lecture. So let me see. So you should have the notes now for lecture 5 on the other one. Let's see if we can just make a bit of an indent into lecture 5. I'll give you a minute or so just to get your notes in order if you haven't seen that lecture. Okay, so we know how to get polymers into solution. We now know how to make measurements on the polymers depending on what molecular weight that we're measuring. We also talked about the molecular weight, or one of the properties, molecular weight, giving rise to chain entanglements. The bigger they are, the more entanglements they're going to feel, and also the thinner the chains, the more likely they are going to be entangled. And that's due to increased secondary intermolecular bonding interactions between the chains, right? So those intermolecular bonding interactions will drive that entanglement even further. Now, what we're also going to consider is chemical structure here. So we're looking at intramolecular, and the key there is it's intra. So it means within a chain. And then we're also going to look at intermolecular bonding, which is between chains. And we're also going to look at this configuration and stereochemistry, and how that the toxicity of these things affect the polymer properties. And then what we'll do is look at the morphology and how that affects the glass transition temperature. So the molecular weight and chemical structure affect 3 and 4, which is the morphology and the glass transition temperature. Also, I'll add into that one, it also affects the TM, which is the melting temperature too in there. And we'll kind of lightly discuss that. So intramolecular bonding within a chain is affected by the repeat unit structure. And it's the types of bonds and atoms in a single chain. So it's the backbone and it's the pendant groups in there. There are 3 different types of chemical bonding. There's covalent, ionic, and metallic. We deal mostly with polymers with the covalent bonding, right? Because we're bonding those to build a chain together. So polyvinyls, you know now, has a carbon-carbon backbone. So most polyvinyls are non-degradable. They have increased carbon content, so they're less polar and more hydrophobic, meaning they're less likely to dissolve in water and less likely to biodegrade or degrade slower. So by adding that carbon-carbon backbone, or having that carbon backbone existing, we know that our polymers are not going to be able to degrade as easily. Now, in contrast to that, we can have polyesters, which have ester linkages in the backbone, and they are more polar, and they're more able to dissolve in water and other polar solvents. So they are biodegradable. So changing that backbone structure has a profound effect on the reactivity of the polymer, if you like. In this case, its ability to degrade. Now, intermolecular bonding is the forces between chains, and these are sometimes referred to as secondary intermolecular forces. And these are what cause the attraction of two different chains or segments of chains from a single chain to each other. So we're looking at, if we've got a chain, we're looking at all this area in between, which is going to be our intermolecular bonding area. Now they're weaker than primary covalent bonds, and they operate at longer distances, so they are longer bonds, and they become more significant when we have a higher molecular weight polymer, which makes sense because as we have a higher molecular weight polymer, we have more regions which are able to undertake this intermolecular bonding, which means that the effect is additive. So when we look at simple bond types, and these are just intramolecular, the carbon-carbon bond is about 347 kilojoules per mole strength. The polarity is non-polar. The bond length, I'm not going to go through all these bond lengths, but what you can see is actually at this top one here where you have silicon fluoride, it's a much stronger bond, and it's polar in there. And it's polar because we have a electronegative atom or electronegative atom on that bond. So in this case, this one will draw electron density towards it, the fluorine. And that's important. Now, when it comes to van der Waals forces, and these are the intermolecular forces, we can list them in order of strength. So London or dispersion forces, which are these kind of, it's the best way to describe it. It's kind of an electron movement. The spontaneous, that's the best way. The spontaneous attraction and repulsion, they have the relatively low strength, and they're non-polar. The bond length is fairly large for those things. Then dipole, so they have this fluorines, but anything that has a electronegative atoms in there is able to pull electrons apart. Pull electrons in the direction of their electronegativity. They are stronger than the London or dispersion forces, and they are polar too. Now, hydrogen bonding, as someone said in the last few lectures, I believe, is the strongest form of intermolecular forces. It's very polar, and it can operate over a relatively large bond strength in there. So you'll see that the intermolecular forces are really crucial in understanding the properties of a polymer, but they become more significant at higher molecular weights of the polymer. So I'm just going to go through the intermolecular forces. I'm sure that you've all experienced these things before. But the London dispersion forces are these intermolecular attractive forces due to small instantaneous dipoles. And it's the attraction between hydrocarbon chains that arise from the changing positions of electrons about a nuclei. So the strongest type in non-polar polymers is things such as polyethylene. We know that one now, really simple one. Polyethylene. So that's the strongest type that, so that only experiences London dispersion forces. It can exist in other polymers with non-polar segments, but other secondary forces are generally stronger. And it's actually how, I don't know whether this has been disproved yet, so you might have to check this, but it is actually an example of how geckos are believed to walk on the wall. So geckos actually have these, what they call cetal areas, and they're like really fine hairs on their hands, which can experience this instantaneous dipoles. So it actually sticks them really strongly to walls because they have such a big surface area, and there is enough force there to hold them up. So dipole-dipole forces are intermolecular attractive forces due to the tendency of polar molecules to align. So the positive end of one molecule is near the negative end of the other molecule. So if we just take this as PVC, if we take this and we look at the electronegative arrangement here, the carbon and the chlorine, there will be a dispersion of charge as the chlorine is more electronegative, so it will pull electrons towards it. And that causes this permanent dipole to form in there, which means that when you have the permanent dipole, just like almost like in magnets, you can get almost a stacking up between those different species there. I've drawn that very badly. Let me just draw that again. So that will be an attractive force, the intermolecular force where that attraction occurs in there. So other polar molecules are things such as the carbonyl, so that has a permanent dipole. The oxygen is electronegative, so it removes electron density from the bond towards itself. And again, the one that we saw before was the carbon and the chlorine, which also has a permanent dipole in there. Now, hydrogen bonding is an attractive force between a hydrogen atom, which is covalently bonded to a very electronegative atom. These electronegative atoms can be things such as fluorine, oxygen, or nitrogen. And the lone pair electron, and it's because they have a lone pair of electrons on the very electronegative atom in there. It's actually water. Water is probably the greatest example of hydrogen bonding. Water exhibits high surface tension due to the fact that these hydrogen bonding occurs in water. And you'll see that how it kind of, I don't know, if you're in your labs, how different it is to pour water compared to many other solvents which flow more readily in there. So that's just an example of the different bonds. I'm sure you've seen those many a time, so we won't go into too much detail there. So let's leave it there for today, and then we'll come back on Wednesday and hopefully complete this one. There's a few interactive bits in this this next sequence of lectures, so hopefully you can all help out with that. And then you'll also get the in-class assignment, I believe, has been marked, so they will get released later on today. And then we probably will get your homework assignments back on Friday, I'm hoping. Okay. And I have office hours today as well, so I'll be available if anyone wants to talk. Good. Okay. Catch you later. Stay safe. You've doubled the capacity since Friday. There was